Okay, so here we have a kind of a ray optics question that I think is one of the single hardest AP questions I've seen, mainly because it relies almost entirely on an aspect dealing with reflection and refraction that we never really talk about in detail. It's true, but most of the time we only sort of deal with these topics separately, and this question requires us to remember that reflection and refraction both happen in every single interface that light passes through or reflects off. And if you don't remember that one fact, this question is essentially impossible, and you'll get maybe 1 or 2 points at most. And if you do remember that fact, then you at least have a starting point. And the other reason I think it's very, very hard is that they give you a text description of what happens, but your first step is to write a huge paragraph sort of explaining that text description. And what I'm going to do first is try to make a drawing that turns that text description into a drawing and then explain my drawing. Because I think that's going to be a lot easier. But they don't ask you to do that, and I don't think that would occur to very many students on the actual test. So the first thing I'm going to do, before I even try to answer that coherent paragraph length description and explanation, is I'm going to draw what happens and see if that gives me some clues as to why. Alright, so we have our bowl, right, kind of like so. Actually, I'm going to draw that a little bit bigger. Right? So that's our bowl, that's glass. Then we have liquid, right? And then above that is air, okay? And we are shining light in. We have, let's use red for the various points of interest that they describe, and we're going to have a point X and a point Y, right? And we haven't shown how we get there yet, but we do. All right, and I'm going to use, I think, let's go with green for the light. So we shine it in here, and that's what we're told, and we have an angle theta 1. Actually, let's see if I can do that a little bit better. That's a little bit better. Not much, but a little bit. Okay, so that's what we have so far. Now we need to figure out what happens and why. Because we need to eventually get light to reach 2 points. And how we do that is going to be, of course, kind of tricky. So the first thing that happens, we go in through glass, and we reach an interface with the glass and the liquid. What happens to that interface? And the answer is 2 things. Because at every interface you get both reflection and refraction. And so some light is going to reflect, right, obeying the law of reflection with those angles being the same. That's how we get to point X. Clearly, if it reflects off that interface, our light would make it to that close point X. But not all of it reflects, right? I'm out of colors already. The light at every interface both reflects and refracts. And we're given the indices of refraction of glass and our liquid, which looks like it's water. And we know that since we're going from a high index of refraction to a low index of refraction, our light is going to bend away from the normal, right? So it's going to end up kind of like that. Right, now I'm going to use green to show the path that it would have followed. Right, that's the path that it would have followed. We're bending away from the normal, though. And so this one I'm going to call theta 2. Actually, I don't know if I want to call it theta 2 because we're using theta 2 later. Yeah, I'm not going to call it theta 2. I'm going to call it theta prime. And all we know is that theta prime is greater than theta 1. That's all that matters for now. And it looks like I'm going to have to move my point Y location, but I'll do that later. So now we figured out what happens with the orange ray. It's done, right? At that point, it doesn't reflect anymore. There's nothing for it to refract free, so it stops. That orange ray is done. But the pink ray keeps going. That's because we're at another interface, this time air and water. And at the air-water interface, just like the glass-water interface, two things happen. The first is that some of it is going to reflect. Right? It's going to go kind of down like that. And once again, use green here. Right. That's terrible. If that's our normal, then this angle, which is going to be actually 90 minus theta prime, I'm just going to call it phi in this case, and that phi are the same. It obeys the law of reflection. But some light also is going to refract. And since we're going from something with a high to low index of refraction, it's going to again bend away from the normal. So it's going to go kind of like off like that. I'm going to use pink to represent the direction it would have gone in, right? And so this new angle, again, doesn't actually matter, but I'm going to call that theta double prime, because we're just making up names for angles at this point. But again, none of these numbers matter. I just want to indicate they're all different. All right, so now our purple ray is now kind of done, right? It's just kind of gone off, however it's going to go off. And we don't really care about it at this point. Right? It's not going to come back in the water. However, our orange ray has now made it to a new interface, a glass-liquid interface. And at this interface, what color should I use now? At this interface, two things are going to happen. Right? The first is that some of it's going to reflect. Right? So it's going to go kind of off like that. If we use green for that normal line, then this is going to be, what's going to be like 90 minus phi and 90 minus phi. Again, the angle doesn't actually matter, but I'm just labeling it for clarity. Some of it's going to reflect. But we don't care about that because, once again, it's not making it down to the bottom, so I'm not going to care about that purple ray either. But some of it is going to refract, and now we're going from the liquid, probably water, back to glass, so it bends towards the normal. Right? So kind of like that. And so now I'm going to move my point Y to match what actually happens, because that's where it is, but the idea didn't really change, right? Clean that up a little, and then, because now we found a second point that hits at the bottom, right? And again, this angle doesn't particularly matter what it is. I'm just going to call it phi prime. Whatever it is, we know that phi prime is less than phi, or less than 90 minus phi, I guess, in this case. Right? So this right here is a horribly messy picture, but it describes, by and large, what happens, that we just need to translate it into words. We've shown how we can get 2 points of light on the bottom, and all we've done is sort of reflect and refract light. And all these different angles, we don't care about numbers, right? That's not the important bit. All that matters is that we know that some of them are the same and some of them are related with greater and lesser things. So, now we can actually do the paragraph. So we want to describe the processes involved in the formation of spots X and Y. And really, all you need to do is go back through. If you missed some of the explanation I did, I've said every single thing as I drew this picture. This has to be your approach on these paragraph type questions. Don't try to just write the paragraph first. Try to figure out what's happening, and if you can figure out what happens, then the paragraph sort of writes itself. Well, why did we get point X? This one comes from reflection, right? And specifically, reflection at the glass liquid interface. Right, that's what causes spot X. That's the process, right? Reflection. Spot Y has a much more complicated thing. I'm actually not going to write it because it'd be a pain. To form spot Y, we need light to first refract at the glass liquid interface, then reflect at the liquid-air interface, and then refract a second time at the glass-liquid interface. Right? All three of those things are required. Right? I'm just going to write 3 steps. Right? Those 3 steps I just said. And then why is spot Y farther away? Well, because to obey those laws of reflection and refraction, since we have to bend away from the normal once and back to the normal once, we travel a bigger horizontal distance, right? It's basically a geometry statement. Explaining that is, I think, tricky without referencing this exact picture that I've drawn. But the idea is to show that because we have to go through all these multiple steps, we've traveled a bigger horizontal distance before we make it back. And then finally, we need to talk about the relative brightness. And basically, the idea is to think about the percentage of light that goes in everything. So point X, we start off with 100% here, and we split it in half once at that interface. So spot X gets a significant fraction of the light. But spot Y doesn't get whatever's left over, right? There's another place where some of it is lost completely, and another place where some of it is lost completely. Right? So at these points, we lose some light entirely, like that's this purple beam. And so spot Y has to be dimmer than spot X, because spot X sort of happens earlier in the process before more of the light is lost. Or sorry, lost is the wrong phrase. Sent in a direction that doesn't return to either point X or Y. And you can make a drawing like this to reference. Right? That can help show the geometry. Like you could make this figure and say, because of all these angles that I drew in the relationship between reflection and refracted angles, spot Y must be always farther than spot X. You have to write and explain it, but this drawing can help. So you shouldn't be afraid to do that if that will make things make sense to you. But as you can see, is the fact that it's taken me 12 minutes to explain this, and this is supposed to be a 20-minute question, it can get very time-consuming very quickly. But on the other hand, it's always better, even if you run out of time, to get the points that you're trying completely correct. All right, so that's A in a nutshell. And if you get A right, the other parts do go significantly more quickly. Not tremendously so, but a bit more quickly. Okay, so now we need to move to path B, or part B. And because I don't want to redraw this whole thing every single time, I'm only going to make modifications to the figure above. And so in part B, we increase this angle, right? So that means we send our light in, I'm going to use a slightly different color of green, at a new, bigger angle, right? That's what we do in part B. Because of that, we're told one spot gets brighter, and the cause must be total internal reflection. So look at this purple line up here. It's already very, very close to the horizontal. If we know to go from this green to this pink, we have to bend away from the normal, and then to go from that pink to that purple, we have to bend away from the normal again. If we make our initial angle, theta 2, bigger than theta 1, this interface, this reflection up here is going to turn into total internal reflection. So your drawing should be essentially this drawing right here, but not this in part B, right? In part B, all the light must be reflected at that water or liquid air interface. That's the point of total internal reflection. And since we no longer lose some of the light at that interface, right, that was what the purple ray was, the light that we didn't get back, the spot Y must get brighter, right? All the light that did previously follow that purple ray now follows this orange ray instead, so we get more of it at spot Y. Right, so you should draw pretty much exactly this diagram, just not this top purple ray that's in the air. That's the one that goes away. right? And the idea to explain why it's spot Y, well, say, energy is conserved, right? So if the light splits into two different rays, that energy gets split. Since it's not splitting into two different rays of that interface, Y gets more of the total, therefore it's brighter, right? And the sketch is more or less what I've already done in that diagram, as messy as it is. So now we're moving to part C. I'm going to use another different color of green. We increase the angle yet again. All right, this is part C. And now we're told one spot disappears entirely. And so, which spot is that and why? Well, remember, we have to bend away from the normal, going through that first interface. And if we make the angle so big, theta 3 big, basically, then we're going to have total internal reflection of that interface already, right? So the light will just kind of go like that. And 100% of the light will do that. It can't do anything else. It's not able to refract to that interface because the angle is so big. And so in part C, point X will move farther out, which is important for your drawing. And everything else, so I'm gonna use, I'm gonna use this kind of yellowy color. Everything else that I drew that's sort of outside, that's in all of this, none of that happens because none of the light goes there, right? This is all X'd out for part C. All you draw is those kind of bright green rays. So the spot that disappears is point Y because total internal reflection happens before that refracted light. Total internal reflection happens to that first interface now. So light never makes it to the second interface to totally internally reflect back down. Right? Out of the three steps that we discussed to form spot Y initially, the first one can't happen anymore. Okay? And so your sketch should just be those light green rays and nothing else at all. And so this right, you saw how part A took me almost 15 minutes, almost 14 or so minutes to do. And then parts B and C, because I had a good sketch and explanation from part A, parts B and C took me about 3 or 4 minutes. So it can be valuable to sort of carefully work through a question, even if it doesn't look like you'll finish in time. Because once you understand what's going on, it's very, very easy to explain little pieces of it, which is what parts B and C are. But this question is very, very difficult. Especially the way they didn't make you do the sketch for what part A looked like. If they asked you to do that and sort of forced you into doing that, then you might kind of have a better handle on it when you try to explain it, and then you're fine from there. But that's the idea, is that this question involves reflection, refraction, and total internal reflection, and sort of the general geometry of the process without ever once doing an exact calculation.